Good morning and good afternoon to everyone. Thank you so much for joining us for today's webinar, Retrofitting of Existing Buildings with Steel Joist. My name is Patty and I will be moderating today's webinar. Today's presenters are Bruce Brotherson with Volcraft and Walt Wordley with Valley Joist.
Hi everyone, thanks for joining us today. We appreciate you taking the time to learn a little bit more about joists. As Patty had mentioned, this presentation is in 3 parts. I'm going to handle the first 2 parts, and then Walt's going to do the heavy lifting at the end. As perhaps some of you know, we've been building joists on the commercial side since 1923, and the Steel Joist Institute was formed in 1928. Consequently, there are millions of open web steel joists in service, and sometimes we need to go back in and reevaluate them and sometimes modify them. So that's what we're going to talk about today. The evaluation and modifications are sometimes required for building renovations. Sometimes there are additional loads applied to the joist. Sometimes dimensional changes in the field causes us to evaluate and modify, and sometimes there's some changes that are not contemplated in the original design, and then sometimes joists get damaged. I've got a few slides which shows joists that can be repaired and joists that may not be. Here's a nice use of joists. This is the rental car facility at the Kansas City airport, and you can see we've got some bowstring girders with rod joists, and it really is a great space and a well used and really a nice use of joists here. I got this picture a few years ago, and the question really is there a fill problem, and did they install this joist at all in the correct way? And so anyway, in this particular case, the question is anything right? You can see the joist has been placed upside down. The bearing seat's not, at the bearing location, and then this purlin is bearing out on the end of the. We've got some in this particular case. Some steel was put in a corrosive environment, and the real question is how do you evaluate that and how do you modify that? Obviously, a new joist is needed, and among some other things. In this particular slide, we show that the joist was placed incorrectly. You can see the bearing seat of that joist, and the joist is actually bearing on the end of the top chord extension. That's not what was originally designed. So we're seeing, in this particular case, we're seeing some deflection in the structure, particularly in the deck, and that's causing us some problems. Obviously, that's something that needs to be closely evaluated. Here's a situation where I don't know what happened here, but the end web of that joist is missing, and obviously that is not a good situation. So something specifically is going to need to be done with that joist to help that joist act as it is intended. Here's another field problem where the top chord section was removed as they were coring the deck. Obviously that wasn't the plan, and so something's going to need to be done to help that situation. The nice thing is that if you look there, it didn't take the vertical leg of the angle, just cut that horizontal leg right off at the vertical leg. So couldn't plan it any better than that, I guess. Here's a situation in a building, a warehouse building, where it was up and functional and had been used for quite a while, and the forklift boom was extended to the top, and it just so happened that it hit the joist and bent the bottom chord. Obviously, that's not the way they come from the factory, and so we're going to need to we did something to fix that a little bit. In this particular case, the guy that was putting in the stud wall, I guess, felt like it was more important to get the stud where it was than and modify the joist, and so obviously that's something that's going to need to be evaluated and modified to get the material that was lost in the top chord to be replaced. Here's a situation where some joists were placed upside down. So the top chord, these were actually square-ended joists. They arrive at the site with the top chord down, and I guess the erector felt like that's the way they should go in place. So they lifted them up and put them in, and it wasn't noticed that it was incorrect until somebody came along later and said, "Whoa, that's not quite right." And obviously, it does matter whether the top chord is down or up, and so the intent is for the top chord to be up. And in this particular case, there needed to be some additional evaluation. This is a slide of a fire. So in this particular building, there was a fire, and you can see that the deck was severely damaged. And quite often, when there's a fire, we get a lot of questions about, about joists and the steel associated with fire, and we'll talk a little bit about that. But generally, if the joists are painted and there's a fire and it doesn't show any negative effect to the paint, you know that the fire was not hot enough to have a problem with the, or that it affected the steel. So if the paint's intact, generally the rule of thumb is that the joist is intact as well. But if the paint is not intact, then some additional evaluation is going to need to be done. Here's kind of an interesting little situation. I designed this building in the 90s. Went back last summer. Actually, as our interns went back last summer, and the guys at this facility said, "Hey, we got some stuff here that we want you to look at." And anyway, they went up in the roof here and noticed that for whatever reason, and I'm not sure why, that the bottom chords of the joist had failed, and in some cases had broken completely. Yeah, obviously, we needed to do something there to help that structure stay up. And as many of you probably are aware, sometimes you're just really surprised that the structure stays up even when there's hardly any structural strength in some of the members. And then, as you can see in this one, that joist there on the right side has essentially no load carrying capacity because the bottom chord has been completely sheared. Here's a situation, I got this picture not long ago where they said, "Hey, we cut some webs out. What should we do?" Obviously, you don't have a joist anymore. You just have a couple angles holding up the load. So obviously, that needed to be fixed and repaired and evaluated, and new web members put in. Here's a situation, obviously, the guys out in the field felt like the girder was a little too long and cut it off and then asked us, "Hey, what should we do now?" So obviously it's better to answer the question up front is, why is the girder too long and what do we need to do to fix it, as opposed to cutting it off and then asking the question, what do we do? So here's kind of an interesting little slide that I come across. In this particular case, the joist was bearing on a masonry wall. The masonry wall was removed to do a retrofit on the building. As you can see, the welds must have been awfully good to the bearing plate, because the bearing plate stayed on, and as they were doing their thing, they pulled the end web out of the joist, and that's what you see there. The bearing seat's still attached to the embed plate, but the joist is obviously very damaged. The good thing here is that they shored up the joist. You can see the jack there, and it shored up the joist, and so there's some opportunity to fix it, or perhaps just get a new joist. But you can see quite a bit of damage was done. I like this slide. you kind of got to wonder what's going on here. You got a relatively small joist, but boy, is that brace big, and boy, is that extra web big. So there's a lot of, I mean, there's some good things that are going on here. You know, we got an extra web in there, we got a brace in there, but the question is, you know, kind of what's supporting what. The brace is big enough to support the joist, and if the load is too big for the brace, obviously, as big as the brace can carry, then obviously the joist is probably overstressed as well. But anyway, it's kind of funny what you see sometimes. Here's a slide we got not long ago, and said, hey, this came to the Ken Charles at the Steel Joist Institute, and they asked him, hey, what do we do here? And obviously, this is probably a joist. This is a joist, but it was not manufactured under the specification of the Steel Joist Institute. So not much that can be done there as far as evaluating it with regard to the specification. Here's a slide we took not long ago as well. These joists actually, they were on a truck and were tipped over. The joist hit the ground, and you can see there's some pretty significant damage both to the webs and to the top chord. So in this particular case, you know, the trucking company wanted us to fix them, to see if we could fix them, and we, in this particular case, said that because they hit the ground, that there's a lot of things going on here that we didn't anticipate, and so the recommendation there was that they just get rebuilt. Here's a little minor damage to the bottom chord that certainly could be repaired, cold straightened, and put back in place. You know, that's a pretty minor situation. Here's a modification that we did an evaluation, and then we did a modification, and then we needed to do an evaluation again because of the poor workmanship of the repair. And so you can see the inspector wrote a whole bunch of things about what he didn't like about that repair. And in this particular case, the repair was probably worse than not doing anything at all. You can see that there are some undercut and some poor welds, and that's always a question now. You know, you're evaluating a modification, and then what do you do? Because a lot of your ability to make a fix or make a modification is taken away with the poor quality that was on this joist. So the Steel Joist Institute has a technical digest number 12, which is entitled Evaluation and Modification of Open Web Steel Joists and Joist Girders. If you're getting into much work, this is really a must-have document. There's a lot of examples, and we're going to just go through a couple of the examples, but there are a lot of examples in the book or in this technical digest, which gives you good idea of how to evaluate joists, and then also how to do modifications. There's a lot of examples there of what to do. We're just going to touch on that a little bit. So in the technical digest, you can see there's a number of chapters and some good information there. One of the good things that's in there is kind of a glossary of terms. And with the joist folks, we kind of talk a special language, and this kind of helps engineers talk the same language. So the top chord and the bottom chord and the webs are noted there. Definition of span is also included there, and then other things like the tagged end, which are really pretty specific to a joist, and then ways that, and then some terms like an end web and main compression web. Things that, if you're talking to a joist manufacturer, the joist manufacturer is going to use terms like this, and just really good information to have so that we communicate well. When we're doing an evaluation of an existing joist, In the best case scenario, we have construction documents, both contract drawings and or the joist erection plan. If we're doing an on-site investigation, we can find the joist tag, and that's really an important piece of information, this joist tag. We'll talk about that a little bit more. But every joist arrives at a job site with a tag. Also, if you can contact the joist manufacturer, quite often they have calculations. That they can provide you of the existing joist, so that's pretty beneficial. And then if we can determine the spec under which the existing joist was designed, that's helpful. Typically, we do that by the year that the joist was manufactured. So if we know what year it was manufactured, then we can kind of back calculate and figure out when we can what the spec was. And sometimes that has some effect on how the joist was designed or what the load carrying capacity of the joist is. In worst case scenarios, we don't have any construction documents. If we do an on-site investigation, there's no joist tag, so we don't know exactly what we've got there. And so in that particular case, one of the nice things to do is to get a joist evaluation form, which is on the website, and contact the Steel Joist Institute for assistance. And here's this investigation form is part of the Technical Digest number 12, and it's also included on the website. And you can see there the address of the website is www.steeljoist.org. If you fill that out to the best of your ability and send it in either to the joist manufacturer, if you know who the manufacturer is, or the SJI office, then you can start figuring out what kind of information you have or what's available. I know it seems in the last couple months or so, with the demise of Shopco, we're getting a lot of requests from people doing retrofits on the Shopco buildings as they're going to be used for some different tenant. And the nice thing about that is, I know in our case that a lot of that information is available from the joist manufacturer, and so that's really a big help. The question is, how do we know what the joists were, kind of the as-built? So if we have original contracts, structural documents, we know what the loads are. We can also get that information from the joist erection plans. Again, knowing what year the job was constructed will help us with the joist specification, this identification tag, and then any field investigation and measurements. Sometimes those are required, but in a lot of cases, they're not if we have the information that the joist was originally designed for. So with regard to joist drawings, there's kind of a difference between the structural drawing and the erection drawing. There are some similarities. The joist designation will be noted, and the joist spacing will be noted. But the one thing that's on an erection plan that's really significant is the mark number, and that's found on the drawing. As you can see, this one is called J11, and then on the metal tag. So on this metal tag, there will be at least 3 pieces of information: the joist manufacturer's name, the joist manufacturer's job number, and then the erection mark number of that joist. So in this particular case, you can see that the manufacturer on the tag, it's kind of embossed in the tag as Volcraft. The manufacturer's job number is 605453, and then the mark number on this particular tag is J23, if you can see that there. When doing a field investigation, things that we want to find is the loading on the joist, and sometimes we can figure that out, and sometimes we can't. The information on the joist tag is mentioned. The joist configuration, meaning what the webs look like and the span and that type of thing. The joist spacing, the spacing between the joists, so that we can calculate what the load for that particular joist was. course, the depth or the height, and then the bearing condition, whether it's underslung or bottom chord bearing, and then, of course, the bearing length of the structural support. That can really, if we don't have enough bearing length, then sometimes that really causes us a problem. When we also doing a field investigation, we want to get some configuration stuff like what the top chord members are made of and the distance between the angles if they're used for top chords, whether there's fillers or ties connecting the top chords together, and then the ties for the double angle webs. Sometimes some manufacturers will manufacture chords using cold form sections, also rods, and then if there's any splices in the chords, whether they're shop splices or field splices, that's good to know. The chord gap, if this was a top chord, there's a gap typically between the chords, and sometimes the webs fit in between there. And I've got some examples of that. The chord gap generally can vary depending on the joist from a ½ inch to 1.5 inches, and so that's pretty significant information. Typically, joists, for most joists, the chord gap is 1 inch, but it can be bigger. So that's a piece of information that needs to be known if you're doing a field investigation. The types of webs, we can have rod webs or crimped angle webs, webs that are welded on the outside of the chords, and cold form sections can also be used for webs. So here's a slide showing rods for the webs. The rods are continuous rods that are bent and then placed between the webs, or placed between the chords in that gap, and then welded in between the chords, and that's typically the way rod joists are manufactured. Here's a photo of a crimp angle web. Essentially, we have a equal legged angle, and then in the manufacturing process, that equal legged angle is crimped or bent so that it will fit in between the chords and welded there. Here's a picture of angles being welded to the outside of chords. So when the forces are significant enough that a single angle won't do it, then we've got to add double angles. And you can see in this particular case, those angles are welded to the vertical leg of the top chord or bottom chord. One thing, or a couple things to keep in mind with regard to field investigation, the end diagonal type is really important. Sometimes those are single members like rods. Sometimes they're double, and so that's important if you're doing a field investigation to note that. Any eccentricities, particularly around the bearing seat, weld sizes and lengths are important to know. So welded connections are sized for the design requirements, meaning the force, the design force in the web, and not the overall strength of the member. So in some cases, you may have sufficient member to carry the additional load that you might have, but we've got to check those connections and make sure that we also got the capacity in the connection and the welds and the lengths. And then also panel point spacing. Make sure that we have what the panel point spacing is, because if we have to recreate a joist, then we want to make sure we got that correct, because that's really important. The weld location is also kind of specific to joists. As you can see in this photograph, you can't see any weld from the chords to the webs, because all of the welds are made in between the chords. And so in that sketch below, you can see where the weld would be. And so to do measurements of welds, you kind of have to look in between the chords, because you're not always going to see it on perhaps the most obvious place on the chords. When we talk about bearing eccentricity, we're worried about that distance. That one slide where the joist was bearing on the end of the TCX, that's kind of an extreme, but quite often if there's some minor movement in walls or the joist, we can get some get some eccentricity in the bearing seat. Typically, joists are not designed for any eccentricity. That work point or theoretical reaction point between the top chord and the end web it needs to be over the bearing condition. So in this particular case, you can see that that's not the case, and we get some eccentricity. Web members also need to be concentric, and so in this particular case, you can see that the eccentricity of the webs is more than it should be, because that reaction point or that intersection of the centroids of the angles really should be on the chord of the angle, so that everything works appropriately and that we don't have induced moments into those connections. When we talk about welding connections, as I mentioned, weld sizes and lengths are designed for the original design requirement and not for the overall strength of the member. However, in 2015, the SJI changed the specification so that all web connections are designed for 50% of the member capacity. That's in tension, and so in some cases this can be a benefit and good to know if your connection is perhaps under designed for the new loads that you have. Other items to note is keep track of the types of bridging and where the locations are, the quality of the bridging connections, and the anchorage of the bridging, and then any interferences, either with the bridging or with other trades, whether it's ducts or mechanical or electrical work. Need to kind of keep track of that, and then the condition of the joist. And the existing deck. Obviously, that fire showed that the deck was in terrible condition and needed to be replaced, but perhaps the joists were not, and the joists could be reused without significant changes. Coupon samples can be used to determine the yield strength if you don't know what the yield strength was. Pretty much in the let's say the late 70s and early 80s, the steel that was used went from 36 KSI to 50, and sometimes when you get joists in that range, we're not quite sure what the steel was. So a coupon is a good way to figure out what the yield strength of the steel was. Here's kind of a little sketch that shows different types of bridging. There's really three different types of bridging. There's uplift bridging, there's bolted erection stability bridging, and there's horizontal bridging. Bolted erection stability bridging is cross bridging, and that should be installed as the joists are being erected before the hoisting cables are released. Horizontal bridging is just horizontal pieces that are welded to the top chord and the bottom chord. Horizontal bridging does not need to be aligned top and bottom like shown in this sketch. Sometimes the top chord and the bottom pieces do not line up, and that's okay. It just depends on how the joist is designed. And then of course uplift bridging near the first bottom chord panel point, and that's to provide lateral stability to that connection, to that bottom chord connection if the bottom chord goes into compression. And that provides that. So if you have uplift or seismic forces, which causes the bottom chord to go into compression, uplift bridging is required. So the Steel Joist Institute, to help organize things, has a 85-year digest, which has all the specifications that have been used. So from 1928 to 2002 is included in that specification, and there's load tables in there as well. So if you have an old joist, this is a good document to kind of figure out what you've got and what the load carrying capacity was intended for that particular joist. In the digest, it kind of gives some guidelines with regard to investigation of existing joists. I like to point out this thing the second point here where it says, the task of investigating steel joists in existing buildings is difficult at best. Personal time, effort, and patience are all required to conduct a proper study. And so, as consulting engineers, you don't want to underestimate the time that this is going to take, because gathering information takes time. Evaluating that information and then evaluating the existing joist is all going to take time and going to be and generally, I think most people would say it's going to take more time than you originally thought. So perhaps a little conservative estimate there might be prudent. With regard to modification of joists, OSHA, particularly joists that are in the construction phase, which OSHA regulates, there's a provision in their code that says no modification that affects the strength of the joist shall be made without the approval of the project structural engineer of record. So quite often, things happen out in the field, and I know we quite often get pulled into those types of evaluations, and we always try to make sure that we're in contact with the engineer of record to make sure we're all on the same page of what needs to happen and how it should happen. There's some methods to reduce the need for the minor repairs. We'll kind of go over that really quick. This is kind of an ounce of prevention for a pound of cure type of thing. And we'll go over the 100-pound rule, add loads, bend checks, and KCS joists. This is a relatively new concept, this 100-pound rule. And essentially what it says is that if the loads are considered perhaps uniform loads, and you have some relatively minor concentrated loads up to 100 pounds, then, and the 100 pounds is applied to both chords in a concentric way, that additional web members do not need to be placed just for these minor 100-pound loads. And so that's a good thing to keep in mind as a relatively new to the industry, that additional concentrated loads, not all additional concentrated loads need extra web members. As long as they're applied correctly and small enough, then the joist will act appropriately without that extra web member. Add loads are kind of a special joist thing. Essentially, with an add load, it's a single vertical concentrated load which occurs at any panel point along the joist chord. This load is in addition to any other gravity load. So sometimes these are called moving loads just because we don't know where they're located. You can call out an add load, say a 500-pound add load, and then the chords would be designed for the worst case, which would be in the center, and then the webs would be designed for the worst case where a load placed at any one panel point. Bend checks are kind of the same. This is so that additional web members don't need to be placed. And so a bend check load, or a bend check would be a load which the chords are designed for, and the chords are designed for in bending, so additional web member does not need to be placed. And these can be in addition to add loads or other loads that are placed. So in this particular case, the bend check is as a load placed in between the panel points, and then the chords are designed for bending. These can be done with both the top chord and the bottom chord. And in the steel joist code of standard practice, there's some nice language that you can use on your structural drawings to kind of indicate that. And this is a good way to explain what you want to do so that everybody's on the same page. So if you have that situation, check out the Code of Standard Practice, and this language is in there. KCS joists are also a different type of joist. They're not necessarily designed for uniform loads, but they're designed for overall moment and shear. And so a KCS joist is really good if you've got mechanical units that you don't know where they're going to be, and you're not going to know where they're going to be. or other loads that you're just not sure what's going to happen. So you can take a safe approach, call out a KCS joist, and hopefully you don't have to do a reevaluation, or at least a lengthy reevaluation. So in these cases, the top chords are designed for the maximum moment in all of the panels except for the end panel, and then the shear is designed for 100% stress reversal in all of the webs except for the end web. It's designed for 100% tension but not 100% compression. So this is a good way to alleviate the need for lengthy repairs and evaluations. And so in this, KCS joists are specified by moment and shear rather than uniform loads. So in Chapter 1 of the Technical Digest, it talks about the evaluation of the strength of joists. And there again, we're talking about the as-built capacity of the joist. The existing joists are possibly overspecified. For example, the 10 PSF collateral might be specified, but there's only 5 on that particular joist. And then perhaps the building usage has changed, and then maybe the joists have been damaged, like some of the photographs that I showed. So to analyze the joist capacity, there's a couple of things to keep in mind. We consider all of the web members to be pinned connected. Prior to 2015, Steel Joist Spec for the K-Series joist permitted bending to be neglected for the uniform loads in the top chord, as long as the panel spacing was not greater than 24 inches. And so that's one of those little subtleties in the spec that we kind of need to be reminded of. In joist, we always consider this a first order analysis. And then the SJI permits eccentricities to be neglected under certain parameters. One is the 3/4 rule, which is in Spec 4.5. And then for all other joist series, when the eccentricity does not exceed the distance between the centroid and the back of the chord. And I talked a little bit about that, but essentially, if the 2 centroids intersect on the chord, then we don't need to consider eccentricity. But if they're off the chord, like in the sketch that I showed, we do need to consider eccentricity. And you can see that's what we've got here, is that there is, in this particular case, we would need to consider eccentricity. So when we're looking at the actual member load carrying capacity, we evaluate the actual member to determine the actual member capacity. Sometimes it's a little more than what was specified. Evaluate any conservative designs and assumptions. Evaluate the length and the placement of weld. I talked about that a little bit. Determine the risk of the repairs versus in-place capacity. I showed in that one picture where they'd done some repairs, and it was actually worse than not doing anything at all. And so sometimes we need to evaluate, the risk of doing a repair and whether it will actually help us or not help us. And then, of course, using engineering judgment. So in the digest, there's an example 1.1 where we're going to look at that and go over that fairly quickly. So in this particular case, we've got a top chord, where we got a rooftop unit that was added to 2 24K7 spanning 40 feet. The unit adds 2 500-pound loads, point loads to each joist, located at 10 foot and 15 foot for one end, and it's been determined that the uniform of the load of the joist is 250 PLF. So determine if the joist needs to be reinforced, and we're going to look at this a couple different ways. So the original design, you can see, is a uniform load of 253 PLF. The actual is 250 with these 2 concentrated loads. So if we do a shear envelope check, you can see that the new loads are going to actually be have more shear than what was needed, or it's going to we've got more shear than what we originally designed for. So there's some questions whether the actual is going to work. It's not a lot, but it's a little bit more, as you can see. So to analyze the joist, we look at the pin. We assume that the pin connections at the webs, and just like we talked about before, we look at the specification, make sure we're on board with the specification, first order analysis, and then look to see if any, whether the SJI permits eccentricities to be neglected, and we can do that fairly easy. We evaluate the actual member to determine the actual member capacity, evaluate any conservative design assumptions, evaluate the length and placement of weld, and determine the risk, and use engineering judgment. Looks like I am getting, oops, I was going the wrong way. I apologize for that. The moment, in this design, we're also looking at the moment diagram. For a 24K7, you can see the moment is a little bit more than what the original design was. And then if we look at the joist diagram, as you can see, the webs, let's talk about the webs first. We got webs starting with web 2, goes to the center at 10, and then since this joist is symmetrical, we've got a 10 R, which means 10 right, all the way to 2R. We've got top chord sections. You can see TC1 through TC18, and then bottom chord sections, BC1 through BC8. And so when we look at our, we do an analysis, you can see that the top chords are continuous in segment 7 through 12, have a larger axial force than the maximum that was in the 24K7. So if we look at that maximum force, let's say top chord section 9, the original force was 26,429, and the new force with the new loads is 29,548. And in these top chord loads, they're all in compression. We're just looking at gravity load cases. So you can see there's a significant load, a greater load in the new loading than what was in the original loading. Bottom chord, same type of thing. We see that segments 3 through 6 are greater than what the original load was. And of course, in the bottom chord, these forces are shown are in tension. Now we look at the webs. So we've got all of these existing webs. And you can see what the forces are. Both, you can see a plus sign means tension, a negative sign means compression, and you can see that the webs, a lot of the webs, forces in the webs are greater. One thing that the specification does require is that all webs have a 25% minimum axial force of the end reaction, and so some of those webs that are in the middle of the joist, where the shear approaches 0, will have more force in them than what the shear diagram shows. And so you can see down there in let's see, web number 8 and 9 and 10. 10R and so forth. That force in the original 24K7 was 1828, and obviously that's not the actual force in the web, but that's 25% of the end reaction. So there's a little bit of extra capacity there. Let's sharpen our pencil a little bit. And the original loads were 20 PSF dead, 30 PSF live, assume a 5-foot spacing, and so the total load in the original was 250. When we look at revised loading, maybe we've only got 15 PSF dead, 30 live, and the total uniform load is 225. So a little bit less. And so this is, you can see what the load diagrams show. So now we look at we look at the actual loading, and you can see that our loads are the delta, or the difference between the actual load and the revised load, is much closer. You can see that for the center sections, we still have 26,429 as the force in the top chord, but in the revised loading, it's not that much more. It's 26,911. So you can see that sharpening our pencil is going to help us a bit. May not have to do as much as what we originally thought. Same thing with the bottom chord. In that particular case, in this particular case, we got about the force is about 3% greater in tension. And so we're getting to the point of really questioning whether we need to do anything or not. However, webs are a little different story. You can see that we're a little bit closer with regard to what we need to do, but there are some pretty significant differences. And as you can see, in some of these, we've got a stress reversal, and that's something that we really need to pay attention to, is that stress reversal. And that's because the shear diagram shifts when we've got those concentrated loads on the joist. So you can see we still got some issues that we need to resolve with regard to these webs, but we're much more manageable by just sharpening our pencil with the loads. We can, for this example, an alternate approach would be to check the manufactured joist using the actual design dead and live loads in lieu of the load capacity of SJI tables. From a review of the structural drawings, the joists are found to be 4'10" on center. There again, we're sharpening our pencil. And check the roof materials, found that the actual roof dead load, including the allowance for the joist weight, is 15 as opposed to what we had before. And then there's the options before we start our strengthening. Can the joist safely support the new loads? There's a bit of engineering judgment that we need to look for. What are the actual loads? What are the actual load cases? And are stress ratios over 1.0 permitted? That's always a good question to ask ourselves. If is a 2, 3, 4% overstress permitted? I'm sure each design office probably has their own opinion on that, but and so that's always a good thing to start with, so that you know what you have to do before you start. There's other options. Particularly if extensive reinforcement is not practical, we can redistribute the loads, we can add a new joist or beam, or we can reinforce the existing joist. So this is not a one-size-fits-all type of approach. There's always options and always things that we need to look at to see what's the best solution for reevaluating and modifying joists. So in the Technical Digest, there is a nice example. We won't go through a lot of detail on this, but essentially what we're trying to do is redistribute the load so that the loads may not be on 1 or 2 joists, but redistribute them so that they're on 4 joists or more joists to reduce the individual concentrated load. So there's 2 design approaches essentially when we do strengthening of joists. One approach is to ignore the existing member strength and simply design the reinforced member to carry all the load. And approach 2 is make use of the strength of the existing member. On small joists, on small situations, it's just easier to use approach 1, particularly on webs, but sometimes with chords, approach 2 is the best. And so we use what works best. Approach 1 and approach 2 can be used on the same joist, just depending on the chord or the web. So when we look at this, we need to consider for either approach, we need to look at a couple things. One is the cost of materials for reinforcement is insignificant generally to the cost of the labor. So material, being real tight on material really isn't going to help us too much. It's safest to reinforce the joist in a shored position. Obviously, we're going to be perhaps cutting and welding on joists if it's up in place, and we need to make sure everybody's safe. Welding can generate enough heat to cause temporary loss of steel strength, and transverse field welds should be avoided because of undercut and those types of things that may damage the existing member. It's best to reinforce the members with dead and live loads removed. Boy, that's sometimes hard. Live loads we generally can get those off, but some of the dead loads we may not. And jack the joist up to the calculated deflection. That's a good way to. There's probably the best way to try to get the joist to as a neutral position as possible, and then of course pay close attention to eccentricities caused by reinforcing. So with the design approaches for individuals, joist members for two, it is assumed that the applied forces are distributed between the existing member and the reinforced member. So direct proportioning of areas is the way that we do that, and we've got a good example in the Technical Digest. If joists are short to remove existing load, we want to know what the preload is so that we can understand what that is. And if the joists are not shored, preload can be calculated based on load present at the time of the reinforcing. You know, maybe 50% of the dead load, for example, might be used. And shoring and jack placement is the responsibility of the specifying professional. This is always something that we really need to pay close attention to, because like in that one slide where the end support was removed, we need to make sure that jacking is done appropriately so that the whole building doesn't collapse and possibly cause injury to people. Okay, so we've got some typical reinforcing details that we're going to go over real quick. It's more difficult to reinforce the top chord, since the floor of the roof deck is usually in place, and overhead welds may be required. Typically they are required, so the workmanship out in the field is going to be really important. On the bottom chord, they're easier to access, and what we want to do is specify welds so that overhead welds are not required. So here's a typical detail. You can see placing rods in the heels of the angles and welding them. That's a good way, easy way to add material. You can see that when the webs are placed in between the cords, you got plenty of real estate there to add material. Here's another example where adding material, some plates. Note that due to the fillet of the angle there in the heel, that plate has been beveled so that it'll fit up tight against both the horizontal and vertical legs. Same thing here. When more material is needed, adding angles to the top chord angles is a good way to do that. As you can see here, welding is going to be a little bit of a challenge, both on that on the outstanding toe of the top chord. That is going to be impeded by the deck, and then that weld on the outstanding toe of the reinforcement angle that's going to be tight up against the vertical leg of the top chord. That's going to be a little bit of a challenge. So kind of keep those things in mind as you're specifying different connections. Here's another option of essentially boxing in the top chord. That works if your top chord's really big and you got a little angle that you can add onto there. Typically in this situation, a rod is, you're going to get more material from that rod, and it's going to be a little bit easier to weld than what we've shown here. But this is a good option. Got some pictures to kind of show what really happens out in the field. You can see the web members are right up against the outstanding leg of the top chord, and that's going to cause a little bit of a problem when we're trying to reinforce that top chord. So in that particular case, we may have to trim the outstanding legs of those webs, perhaps at a 45, so that we can get those reinforcing into the top chord. Here's another example where we may have to cope or notch the reinforcing plate, and you can see here that the webs are going to be interfering there, and that we're just going to cut that plate around the web so that it'll fit in tight onto the top chord. One thing to keep in mind is if we've got we're putting material into the top chord, and that material needs to be continuous, we may need to reinforce or splice the additional material so that it can be continuous. Something to keep in mind. In bottom chord reinforcement, like I said, it's a little bit easier, so a plate on the bottom chord is always a good solution. And in this particular case, you can see that weld does not need to be, if you extend the bottom chord out past the toes of the chord, then you don't need to use a overhead weld, and that's probably the best way to do that, to make sure that everything is fits up well and that the welding is the best possible. I mentioned this a little bit before, but web members that are welded are generally in between, or these crimped members are generally in between the chords, and this is where the little bit bold line there on those web members is essentially where those welds are going to be. And so sometimes you just need to measure, have somebody or do it yourself, is measure how much weld you actually have, so that you can determine what you may need to add. And so this slide is just meant to say this is where the welds are, this is what to expect, and if there's questions, they're going to need to be measured in the field. For rod reinforcement, if you got a rod web, it's really easy to put an angle on the outside of the chords. You may have to trim them so that you get so that you don't have excessive eccentricities and that they fit up better, like what we show here with this top chord. And you can see a rod reinforcement is there. Quite often we'll have, at least on the details that we do, that these types of things need to be measured in the field and cut appropriately. Here's an example of that. You can see that simply just putting an angle on the outside of the chords adequately reinforces those webs. And you can see that that's a fairly easy way to do that. Here's a situation where we've got some crimp members, and we've got some things going on there, so we've kind of got to be aware of that. When we got crimp members, there's a couple good ways to do that. Again, putting those additional webs on the outside of the chords, but we want to snug those up as closest to the crimp member as we can. You can see what we've on that sketch on the right there, that we have them close enough that we can tack them, and this helps both with the alignment of the web so that we don't have excessive eccentricity. But this is a common way to reinforce crimp members. And here's a picture of that. As you can see, that additional web member is really tight up against the crimped member, and then welded up to the top chord. When we've got some real challenges, this is a detail. We don't see this used much, but this is a good detail. If you've got some challenge is to try to get some weld on there. You can see that a plate is attached to the crimp member, and then additional rods are attached to the plate and the top cord to get the force into the cords. When we got double angle web members, an easy way to reinforce that, just like at the top cord, is to place the rounds in the heels and then weld those up. The welds don't need to be continuous; they can be intermittent, depending on the size of the rod member and what you're trying to do. But we typically just use enough weld to make those a composite section. Here's an example of that, and you can see they're not continuously welded. They're just welded intermittently so that those two pieces act together as a composite section. There again, end diagonals. I mentioned this a little bit earlier about the end diagonals and making sure that we know what we've got for end diagonals, because if we're doing a repair, we really need to tailor the repair to the actual member size. And so in this particular case, there again, if you got a rod end web, then you can add a reinforcing angle on both sides and get significant more capacity out of that. There again, if you've got some problems getting some welds, this is a little detail that shows how to get a little more weld capacity on a rod member if you just need weld capacity. When we look at reinforcing versus replacement and adding, the cost of the field repairs is going to be lots of money compared. That's where most of the money is going to be. Time is money. We need to look at the difficulty of the repair, interferences and access points, effectiveness of the repair. You know, what we're doing is, are we really adding capacity, or are we just essentially just putting stuff on the joist that may or may not have our desired effect? And then, of course, the skill of the workman. So a couple of these things, and when we're talking about reinforcing versus replacing, that's reinforcing the joist or replacing the joist or adding a new joist. And so existing interferences we got to be careful of, piping, electrical conduits, removing or relocating. These interference could be a greater expense than the reinforcement itself, so we need to watch that. Camber is also something that we need to typically be aware of. The joists are typically built with camber built in, and so if we're adding a new joist, we may need to provide less camber in the new joist because the existing joists are going to be deflected, and then new camber is going to be, if we provided the standard camber, that may not work in that situation. Joists can be ordered with a shallower seat depth so that they can get into the bearing and then shimmed up in the field, and joists can be supplied with a splice, a center splice, so that there's two individual pieces that can be installed and bolted together, so that they're a little bit easier to handle, particularly in buildings that are occupied or that you have a lot of interferences with. So when we talk about camber, as I mentioned, we've got some, the joists are typically cambered, and then after the dead load's installed, then the joist will deflect a little bit, and sometimes they'll be flat. Not always they'll be flat, but they'll be flat. So if we're replacing or adding a joist, we need to keep that in mind. So we can have a splice. We call this a field splice. So you can have two separate joists, two separate pieces, and then you wiggle them into the bearing situation, then you can bolt them together. That's sometimes a real good solution. When we talk about the bearing seats, we typically, like for an LH series joist, we've got a 5-inch bearing seat. The new joist can be built with a shallower bearing seat. In this case, we show 4 inches, and in that particular case, you can see there's a gap between the top cord and the deck, so it's not quite is down a little bit, and then we can, with the new joist, we can put some shims under it to get it right up to the deck and support the loads from the deck. When we're looking at replacements of joists, we need to look at the lateral stability of the joist. Typically, the top chord lateral stability is provided by the deck attachment, and so if we're doing a replacement or adding a joist, we need to be very careful about how that top chord is going to be laterally supported. So we can shoot pins through the chord or the deck or the slab, or we can add more bridging to that new joist so that so the bridging adds the lateral support, and the joist is designed for the unsupported length between the bridging. So that's kind of a major issue that needs to be addressed when we're talking about replacement and adding. When we're reinforcing the existing joists, for reinforcing webs can be easily added on the outside of the chords, like we demonstrated, and chords are typically thin angles. So make sure that when you're adding the welds, that the welds are not so big that they're going to be difficult for those thin chords to handle. So typically on a rod web joist, a maximum of a 1/4 inch fillet, even a 3/16 fillet is probably more appropriate, but a maximum of a 1/4 inch fillet is probably appropriate. Crimp angle web joists, there again, the reinforcing webs can be easily added to the outside of the chords, and if the chords and webs need to be reinforced, there could be interferences which affect how the reinforcement is done. We showed a couple of little details on that, and I hope that was self-explanatory. For larger LH series joists and joist girders, double-angled diagonal webs may intersect at the bottom chord panel point. There's not room to add and weld reinforcing to that panel to pick up the load, and the load may have to be checked for bending, for local bending. So typically what we would like to do is to add additional web members, but sometimes that doesn't work out so well. So maybe these web members need to be coped special to get in between the gaps of where those webs are. And sometimes it's just easy to check the chord for bending, particularly if the load is not in the center third of the joist. The joist may have sufficient capacity without adding an extra web to carry that load. So there again, something to keep in mind. The following will impact reinforce of both the chords and the webs. The chord and web yield strength, like I mentioned kind of before, recent manufacturing, 15 to 20 years, we've used 50 KSI steel. Older joists have been manufactured using 36 KSI material, and so sometimes we need to do test coupons to determine what the yield strength would be. If you talk to a joist manufacturer, if you got that year of manufacture, and you talk to the joist manufacturer, they'll probably have a pretty good guidance of whether they were using 50 or 36 KSI material at the time. One thing to keep in mind if you're giving direction for people taking coupons is a good place to take those coupons is at the end of the bottom chord beyond the first panel point, because theoretically there's no force there, and removing a little bit of material is not going to be a problem. I had a situation where they took the coupon in the bottom chord out in the middle of the bottom chord. Unfortunately, after that was done, then we needed to reinforce the bottom chord. So it was kind of a little forethought would have helped in that situation. When we talk about deflections, deflections control is often required in addition to the strengthening of joists for the load, particularly floors or some roofs. And so we need to consider the deflection when we're looking at the joist. So a live load deflection of less than 240 may not be met if the joist is only strengthened for added loads from snowdrift, for example. So keep in mind that, of course, we need to carry the forces, and then we also need to to manage the serviceability. Sometimes that's important, sometimes it's not. When shortening or lengthening joists, cambers need to be retained when removing any web members. We've got some good examples in the Technical Digest about shortening and lengthening joists, and it's kind of, you got to sometimes give a procedure of how to do the repairs so that camber's not lost. If you remove the webs, let's say you have two webs, you move them both from one side of the joist because they need to be bigger, you're going to lose camber, and so that's something to keep in mind. Bridging for additional loads. Bridging may be needed or added to modify, provided the required lateral support of compression top chord is critical. Like we talked about when we're adding joists, we need to be aware of that. And bottom chord may be subjected to compression during uplift. That's, a few years ago we were not designing all joists. Like, for example, in California, we weren't designing joists in California for uplift. Now the new code says we are going to, and so if you're looking for existing joists, joists that were built maybe in the 90s in California did not have uplift, but now if you're looking at the new code, they're going to need uplift capacity, so that's something to keep in mind. And then refer to the SJI specifications for bridging requirements. When we talk about if we're going to add an additional support to a joist, we need to be really careful with that. Additional supports can be added to joists to increase their capacity, essentially decreasing the span, and this will drastically alter the wedge shears and may cause load reversals in the webs. If we move the support point, we are definitely going to alter the shear diagram, and may cause us some problems with regard to the webs. If the support is added between the bottom chord panel points, like what we show in point B, reinforcing webs must be added to support the bottom chord. Obviously, that is a bending load. Without the additional webs, that's going to be a bending load in the bottom chord of the joist, which generally probably is not going to be